It's a very nice summer afternoon here, so thank you very much for being here today. We are very glad to have the visit of Professor Chris Boyce. For those who don't know me, I am Professor Mauricio. I am with the Chemical Engineering Department and also with the Chemical Engineering program here. And so today we are very happy of having this presentation from Professor Chris Boyce. He is with the Department of Chemical Engineering. He is an associate professor there at Columbia University. He has been with Columbia University for 6 years now. And he is a chemical engineer. He graduated from MIT, and his graduate studies were at Cambridge University. And when he defended his PhD, it was considered the best PhD thesis that year. And he has held some postgraduate positions at ETH Zurich and also Princeton University. And he works with, for example, with the physics of multi-phase and granular flows. He has received many awards, including one from AICHE, and he was named for the list of the 30 list under 30 from Forbes. And today he is going to present the lecture entitled Structured Flow Instabilities in Excited Granular Materials. So thank you very much, Chris. I will pass the microphone. Thank you again.
Okay, great. Thanks, Mauricio, for that very kind introduction. Everybody can hear me? Great. And so, yeah, and thanks to Fabio and Priamo and everybody who's made this, invited me here. It's been great to see more of the city. Rio's an absolutely amazing city, and of course, we're having a lot better weather here than up in New York right now. You may see lots of snow and such, and it's been great to just, so far in 1 week, get to meet so many people, and I'll be here all week, so I look forward to meeting even more people and seeing more facilities and such in this week. So yeah, today I will be talking about structured flow instabilities in excited granular materials. Here what we can see is just a preview of seeing gas bubbles rising in a structured manner through granular materials. So when I say granular materials, you can think like sand, for example, if you're trying to get an understanding of that. And so yeah, without further ado, I'll get into the bulk of the talk. So to give an overall outline, I'll start talking about some of the physics of different instabilities and different flow behavior within granular materials. I'll then get into some motivation as to why, as engineers, we should care about the physics of granular flows. And then I'll take the majority of the time talking about how we induce structured flows within granular materials, as well as develop improved ways of modeling computationally these flow behaviors in granular materials. And then I'll take a little bit of time to say how we're going beyond granular materials into dense suspensions to try to achieve some of the same structured flow phenomena within dense suspensions. And then I'll end with some short conclusions. So first of all, starting about the physics at play here. So if you think about granular materials, it's very tempting to view them in a lens of being similar to a liquid, because as you can see in an avalanche of granular snow, it flows down in a way due to gravity in ways that are very similar in many ways to water flowing down a hill in a river or so. We also have a phenomena where if we blow gas up through granular particles like glass beads, we get bubbles which rise through them, similar to what happens if we blow gas up through a conventional liquid, of having the gas rise in the form of bubbles. But there are key differences between granular materials and conventional liquids. So there's no yield stress within in a Newtonian liquid like water, and thus it'll just spread out, unable to form these 3D structures that form, for example, in a sand pile due to the yield stress effectively that exists within granular materials. And also, under gravity, grains will pack at a high fraction, and there's strong gravitational forces and frictional forces between the particles. So if you very carefully put together sand of different colors to create this dog face, unless you do something violent to shake it up, that dog face is going to live forever. Whereas if you try to do the same thing with food coloring in water, for example, then you would quickly have self-diffusion in that to quickly spread out all the different colors in this dog face, and you would not be able to hold that for any significant period of time in a conventional liquid. So on that front, you could start to say, okay, well, maybe granular materials are more like solids than they are like liquids. So you can create this dog face in a granular material, and you can also create a dog shape in Legos or so in a conventional solid. You can also create 3D structures within a granular material, such as a sandcastle, in the same way that you can take larger discrete solid particles and put them together into form a 3D structure. But what's some of the differences? Granular materials, when we conventionally think about them, are small enough that they can fit into the geometry of a container. So if you have a glass, if you have a glass and you fill it up with sand, the sand will take on the shape of that container. But if you had a solid object that's much larger, it wouldn't be able to fit into fit the shape of the container. And the grains also tend to be small enough that they can shear past one another, as we have in an avalanche, whereas if you have just a solid object like a sled, it will retain its 3D structure, and the different components of the sled won't shear past one another when you go take it down a hill, for example. And so then we can say, okay, well, what are some other types of things that are somewhere in between a solid and a liquid? And so we may think of a colloid, for example, in which you have these randomly moving around different particles suspended in a fluid, typically, like within milk. And so the random motion of these particles has also been shown that if you vibrate metal spheres, you can also get these random diffusive moving behavior. But the difference between a colloid and a granular material is the granular material is typically larger than 10 microns in size, and thus thermal energy from KBT is not strong enough to induce diffusive motion in the particles. So when you have this collection of granular particles, KBT is not strong enough to get the particles to move around, but if you have a glass of milk, KBT is strong enough to get the different milk particles to move around in the system. And so we typically say that granular materials are greater than 10 microns roughly in size, whereas colloids are less than 1 micron in size. That creates this difference in thermal energy affecting the systems. So we can also think about dense suspension, so different larger particles suspended in a liquid. So they both involve small particles which are too large for thermally induced motion. They both can transition between apparent fluid-like behavior into apparent solid-like behavior, for example, under shear, where the particles will become too close to one another and they'll jam together, as it's called, to all move together as a whole rather than being able to move past one another, as shown for both dense suspensions and grains. And but there are some differences. So in a dense suspension, we have surrounding liquid, which tends to reduce some of the gravitational effects and frictional effects, which occur more in granular materials. And you usually need some other type of excitation to get dense suspensions into a solid-like state, whereas sand and granular materials in general tend to be more inherently under gravity in a more solid-like behavior. So I guess what we've seen is that granular materials take many different forms, and they can't be, simply described as just a solid or just a liquid or analogous completely to colloid or a dense suspension. And what we also can learn about is that there are various instabilities which can be seen in grains, some of which are similar to liquids, some of which are similar to solids, some of them which are not seen in any conventional liquid or solid. So what we can see here is that if we are rotating this inner part of a inner cylinder, that's going to create a shear within the granular flow. And at above a critical shear rate, the particles actually form these force chains, as they're called, where they get locked in together with one another and begin to move around totally as a solid. So in this way, the shear jamming phenomenon is similar to a solid. You can also have two types of grains shearing past one another, white grains and black grains as depicted here, and they form these wavy instabilities on the surface of the grain, and that would be similar to air flowing over water and forming these wavy instabilities on the surface of a lake or a sea or so. So in this way, we can see some of these instabilities can be similar to a fluid. And we can also shear grains in such a way, if we've got gas flowing up through them, we call the particles as fluidized, as suspended by the upward gas flow. And you can see that you can form these counter-rotating vortices, which are analogous to those seen in the classic Rayleigh Taylor-Couette vortices seen in fluids. We also have gravity-induced instabilities within grains. So if you have a large silo of granular material, it often is a problem where these arches can form, and even though you've opened up the bottom of the silo, the grains are not pouring out. And so these arches forming make the material behave almost like a solid. It's not going to pour out because of these arches until you disturb them. You can also see for example, in an hourglass, you can have sand flowing out the bottom of an orifice, and people have noticed that due to small cohesive forces between the particles, the stream, while starting out straight, will eventually break up into droplets, similar to the Rayleigh plateau instability seen, for example, when you have a leaky faucet or so, with starting out with a straight stream that then breaks up into droplets at the end. So again, we see both solid-like and liquid-like behavior when gravity is acting on grains. We can also excite granular particles into a fluid-like state when we vibrate them from the bottom, and we can see the particles move around in a random walking diffusive manner. And this is analogous, actually, people have shown, to the random diffusive motion of molecules within a gas. And further, we can see certain, known in America at least as the Brazil nut effect, certain aspects of having two particles of different sizes tend to segregate, usually with the larger particles going to the top when you vibrate the system over time. So this doesn't have an analogy to either a liquid or a gas or a solid or so, but another interesting phenomenon that we'll somewhat explore further of how can you get particles to either segregate or mix is one of the goals we'll ultimately have in this work. And we can also have instabilities introduced by flowing gas up through granular particles in what we call a fluidized bed. So typically what we can see is that when you fluidize the particles, you get these bubbles of gas rising through the particles, even though there's no real surface tension between the liquid and between the particles and the gas, as there would be if you blew air up through water, for example. We also have these, if you go to even higher gas flow rates, you can see clusters of particles formed together, again, even without the need for cohesive forces or surface tension or anything like that in the system. We can also, by blowing gas up through particles, tend to segregate particles, usually with the lighter particles or the finer particles going to the top and the heavier particles going to the bottom. And again, we're going to explore this further in the talk of, okay, how can we use the vibration and the gas flow to get the desired flow behavior that we have within grains. So all of that was a very long introduction, so thanks for taking the time with me to go over that, but just wanted to get everybody on the same page as to what we're going to be talking about. And so the key takeaways are that, first of all, it's just fun for me, at least personally, looking at these different instabilities and trying to figure out how they work. And we can get the particles from a solid-like state into a fluid-like state either by vibrating them or blowing gas up through them. And so we often see phenomena that look similar to what we see in fluids, but oftentimes the underlying mechanism is different, such as in the bubbles that you saw earlier. And we have also seen that we can have these transitions between solid-like and fluid-like behavior that we're going to talk more about later in terms of creating instabilities in grains that are not seen within within fluids or solids alone. And then what we're going to investigate more is how can we use all of this to manipulate the segregation or mixing of particles into a manner that is desired for different applications. So now if we go on beyond the physics into the engineering aspects, we can see some of the ways we want to use this. So we can think about conventionally you would tend to carry out chemical reactions within what we call a packed bed, in which the particles are all, you've got catalytic particles, they're all stationary, and you're blowing up liquid or gas through these particles. The problem with packed beds, if you have a very exothermic chemical reaction, is that you can get some areas become very hot, dangerously hot, other areas stay cold, and you don't get a uniform temperature throughout the reactor, and thus you often have issues with getting optimal reactor performance and safety as well. So to combat this, 100 years ago or longer, people figured out that you can actually go to a gas flow rate that is high enough to suspend the particles in what we call a fluidized bed, and these bubbles rise through the system, and they act to mix around the particles and can behave in such a way that you can achieve a uniform temperature distribution and avoid the hotspot issues of packed beds. The downside is that if you have these large bubbles moving through the system, you may not get all the gas to come into contact with the granular particles, and thus you may lose out on some of the chemical reactions. And also, fluidized beds have been notoriously difficult to scale up from the laboratory to the pilot to the industrial scale, because the behavior of these bubbles changes as you change the size of the system. So many different chemical engineering projects have taken way too long to build and operated in a inefficient way in the end if they've used fluidized beds, because people have been struggled really in controlling the motion of these bubbles. So what we're going to try to do here is use both vibration and gas flow to get the same predictability and scalability that people generally have when they use packed beds, but sort of get the best of both worlds between packed beds and fluidized beds, because we still want to have the particle motion and mixing and rates of heat transport of fluidized beds to create uniform temperature distribution in the reactor. So that's one goal of this work. We also have other applications beyond chemical reactors. So it's now becoming clear that we're going to need to mine quite a bit of silicon, lithium, and copper for different things like solar energy, batteries, all different aspects of getting a clean energy future. But actually, about 10% of global energy right now is used to just grind down to micron-sized particles all the different things that are dug out of the earth in mining. And then also tremendous amounts of water are used to be able to separate out the useful and the useless from the useless particles in a process called flotation. So the combination of grinding and water use needed for the current mining separations is, and as we scale up our mining in the future, is really problematic for a clean energy future. So, another thing, if we can separate granular particles out, we don't have to grind them into micron-sized particles. We can alleviate most of the energy use, and so that's another motivation for this work, trying to be able to separate out granular particles based on their size and density and reduce the amount of grinding that's needed for mining separations. We also have, so they have the opposite problem essentially in the pharmaceutical industry, where you need to have the exact right amounts in each tablet that you make of the active and passive ingredients within granular, within these mixtures. And so a variety of devices have been created to try to perfectly mix these particles, but it still remains, it ends up taking up a lot of time and energy to create these tablets at the end. So another goal we have is to optimize the mixing within a fluidized bed to potentially have that used in order to create tablets for the pharmaceutical industry. And finally, we have the goal of being able to model all of this at the industrial scale in a predictive way. So we'll talk about a few different types of computational modeling tools that we use in my lab and we develop. One of them we call CFD-DM, and in that case we're using CFD, computational fluid dynamics, to simulate the gas flow, and we model each individual particle following Newtonian mechanics as it moves around in the system. The problem with this methodology is that you can only use it to model laboratory scale systems. It's too computationally expensive to model an industrial scale system. To go to the industrial system, we can't model each individual particle because there might be over 1 billion particles within an industrial scale system, and thus we need to model the solids phase as effectively a continuum, and we need to come up with a rheological model that is able to capture these dynamics. And so it ends up being a highly non-Newtonian rheology needed to model this. And we've already gone over the fact that we can have both these densely packed solid-like behaviors of regions of reactor behavior and these fluid-like, less densely packed regions. So we need to capture a rheology. We need to design a rheological model that can capture all of this at the same time in one system. And so that remains a very, to get an accurate industrial system, we need to design these rheological models, as we'll discuss in the future. So overall, we want to get controlled convection, controlled motion, and predictable motion and scalable motion of granular particles that avoids this issue of having the dynamics completely change when you go from the laboratory to the industrial scale. And we want to be able to either, in some cases, segregate out particles from one another, and in other cases, mix them, depending on the application, depending on the industry. And we want to make sure that the motion we get induces a uniform particle temperature distribution to avoid the issues of hot spots that we have in packed beds. And we ultimately want to get a good continuum model for granular flow, which can capture both the solid-like and the fluid-like behavior of grains so that we can get accurate industrial scale models. So that's what we want to do. So hopefully that lays the framework for motivating exactly why we want to study this. And now we'll get into the bulk of the material, which is on the different structured flow instabilities, which we've developed in my lab over the last 6 years. So to put it all in one slide, we can see we're going to look at different dynamics at different gas flow rates. And we see that at low gas flow rates with vibration and gas flow, we can get the particles to circulate around in this repeated pattern that we show is analogous to Rayleigh-Benard convection in a fluid. we show that at an intermediate gas flow rate, we can get these wavy-like patterns to form, which we've shown have been analogous to the Faraday waves, which would form in a glass of water if you shook it up and down. And at higher gas flow rates, we get bubbles, but we've shown the ability to get the bubbles not to move chaotically, but to be of uniform size and to rise in this triangular lattice shape, which we describe as structured bubbling. So this is basically the different instabilities we're going to show more systematically slide by slide for most of the presentation. So to give it a sense of what experimental setups we have, so we have gas uniformly injected into the base of the system through a porous plate, and then we have the entire system mounted on top of a shaker to induce the vibration in the entire system. And we have both these pseudo 2D fluidized beds, which we can look at from the side, and we also have a fully 3D fluidized bed that we can look at from above with the camera. So that, and so we're controlling the gas flow rate, we're controlling the frequency and amplitude of the vibrations with the shaker. And we're all going to be looking at, what I'm going to show you here are spherical particles in the range of densities and diameters relevant to a number of different industries and such. Keep in mind we're in like the 50 to 500 micron range for the particle sizes. And so what we've shown, one of the first things we looked at when we started to combine this gas flow and vibration was this ability and when we normalize the gas flow rate by a minimum velocity needed to suspend the particles, and we normalize the vibration strength by the minimum needed to suspend the particles with vibration on its own, we noticed that combining gas flow and vibration, we were able to create this fluidized state where the particles move around, but no gas bubbles rise through the system. Whereas if we use only gas flow alone, as soon as we fluidize the particles, as soon as we get them to stop being stationary, we immediately have gas rising through the system. So we're already starting to see this this ability to get particles to move around to avoid the issue of packed beds, but at the same time, avoiding issues that occur in bubbles in fluidized beds. And so we also noticed that within this bubble-free fluidized state, we could get the particles to form these regular convection patterns. And if we make the system twice as wide, we just get twice as many convection rolls. And we essentially see, if we make it twice as tall, we just get wider convection rolls that form. And so we're also seeing some advantage of having the particles move around, albeit fairly slowly, which will be helpful for heat transfer, but at the same time, having the ability to, avoiding issues of bubbles rising through the system. And so we demonstrated through computational modeling that, oops, bad idea. We demonstrated through computational modeling that these convection rolls are actually formed in the same way that happens in the Rayleigh-Benard convection phenomenon. When you heat up a liquid from below, if you heat up water, for example, the thermal expansion will lead to there being a low density in the hot region and a high density in the cold region, and that buoyancy causes the hotter fluid to want to rise to the top and the colder fluid to flow down, and the competition between this buoyancy and viscous forces leads to these regular convection patterns that are called Rayleigh-Benard convection. We've shown using two-fluid modeling here that we can recreate the convection pattern seen in grains. And what we see here is that, we see here that because of the vibration of the grains, the particles are pushed away from this bottom layer. And what that yields is a difference in the particle packing in different ways, which yields a different bulk density where you've got a low density at the bottom and a high density at the top. And so due to buoyancy, these particles at the bottom want to rise, and then due to frictional forces, between the frictional forces between the particles, that it behaves as an effective viscosity between the particles. And so this competition between buoyancy and viscosity, again, we've shown yields the structured convection patterns, which are exactly analogous to Rayleigh-Benard convection in conventional fluid. And we've shown that in 3D we can get even more interesting convection patterns to form. My mom has told me a few times that she thinks this looks like a brain or something like that from the top. But you can see each one of these is a convective cell that is forming. And so we can see in 3D as well the pattern, the ability to create these regular convection patterns still holds, albeit more complicated geometry forms. So next we also looked at, in this bubble-free convection state, bubble-free fluidization state, what happens when we put light particles, which are slightly larger than heavy particles, and we put light particles on bottom and heavy particles below. And so what we end up seeing, okay, unfortunately, the video seems to have not loaded for this one. Let me see if it's somewhere else. Okay, so it looks like it's just not working, unfortunately. Oops. Oops. Okay. Well, that's unfortunate, but essentially what happens is the particles, the light particles rise up in the form of these, what we call fingers and granular bubbles, and so ultimately you get all the light particles going to the top and all the heavy particles going to the bottom. And so we've shown, so the pattern that forms is similar to what's seen in, if you had oil and water mixing together, how the oil would rise to the top, and it's and we've shown that it's it looks very similar to what we call the Rayleigh-Taylor instability in conventional fluids. But one thing that puzzled us is that there's no surface tension, there's no strong cohesive forces between these different particles. So why do we get something that, so the Rayleigh-Taylor instability occurs due to a competition of buoyancy and surface tension. So we wanted to know, why is this occurring nonetheless? And so what we have seen is that we could recreate this with the CFD-DM simulations, and it shows these finger-like structures forming as the grains rise through. And what we could see in the simulations that we can't see within experiments is that the gas flow that occurs, and we see that gas channels through these lighter particles, and this gas channeling through these lighter particles leads to an increase in the drag force on these lighter particles that acts to push them up. And so this increased drag force acts to counterbalanced by increased contact forces pushing the particles down. All this we can see in simulations, not in experiments, but they show that it's actually this gas channeling through the lighter particles, because they're also slightly larger than the heavier particles, is what creates this aspect that takes the place of surface tension. So this is another example where we see a phenomenon similar to in conventional fluids, but the mechanism underlying is slightly different from a conventional fluid because there is no surface tension. And so we've seen this when we put a smaller droplet, as we call it, of the heavy particles surrounded by a sea of the light particles, we see another interesting phenomenon where the particles undergo these binary splitting events over and over again which occur in them. And so this we've shown occurs because the particles directly below the granular droplet enter a solid-like region, solid-like behavior because gas channels around the solid particles. And so instead of descending directly through a solid-like region of particles, the granular droplet has to spread out to descend through the still fluid-like region of grains to the side. And so we've shown with particle image velocimetry what's occurring here. So the particles directly below the granular droplet have essentially no velocity, no speed, and which indicates that they're in this solid-like behavior, whereas there is motion in the particles to the side, so they're still in a fluid-like behavior. And of course, it's easier to descend through a fluid than it is to descend through a solid. So this is an interesting phenomenon for us to investigate because it now is involving this transition between fluid-like and solid-like behavior in the grains. And so what we showed is that with the discrete particle simulations, because you're modeling each particle individually, it can account for this splitting up of the granular droplet, and it inherently captures the phenomenon we see experimentally. Whereas when we use the continuum simulations, they're not able to capture this solidification of the particles, and so they show qualitatively the wrong behavior. They don't show the splitting at all. So this motivates us to find a way to improve the rheological model for the continuum simulations to be able to capture the splitting. And we have had a paper where I'll get to it later, where we find ways to improve the rheology and capture this solid-like behavior. So what are our takeaways from the bubble-free fluidization? So we like the ability to segregate particles, but the motion is very slow. So we want to find ways to either mix particles or segregate particles in a faster way than we do in the bubble-free fluidization state. And so it's interesting to create these structured patterns as well, but we also want to see, can we develop a rheological model that can capture these fluid to solid transitions? So we try to address some of these problems by now going to a higher gas flow rate and looking at, in this fluid-like state, at the higher gas flow rate, we get these wavy convection patterns that we show are analogous to Faraday waves in a vibrated liquid. And both of our simulation techniques can inherently capture these dynamics because there isn't any issues with transitioning to solid-like behavior within the Faraday waves. And so what do we like about these wavy dynamics? So we can now get better scale up because the wavy patterns form and they look essentially the same even as we make the system taller and taller. So we can get predictable scale up in the behavior. We also get predictable flow behavior because every 2 vibration cycles, the wave pattern repeats itself. And so we can get more predictable structure within the system. And we can also get control over the dynamics. So if we just increase the frequency, we decrease the wavelength and the wave amplitude. So we have more elements of control if we want to have a lot of convection versus less convection, for example, we can change the frequency. And also as we scale up the system to the side, we maintain, if we make the system twice as wide, we still get the same wavy patterns to form with the same wavelength and amplitude. So again, for both vertical and horizontal scale up, we get predictable behavior, so we can avoid some of the issues with scale up of fluidized beds. And if we go into 3D systems, we can get even more interesting convection patterns to form, and we can again be able to know from the beginning based on what amplitude and frequency we're vibrating at, which one of these patterns we're going to get in the system. And so we've also tried to find ways to, to be able to predict or to be able to put this in non-dimensional terms for providing more design rules to help out with industrial practitioners know exactly what behavior they're going to get. So we noticed that as we increase the gas flow rate, we decrease the vibration strength needed to induce these wavy patterns. And we can combine the gas velocity and the vibration velocity into one dimensionless parameter, which collapses these data across many different systems onto a fairly uniform curve. And the last thing we saw that with this is if we start out with a mixture of heavy and light particles, we can still form the wavy patterns. It doesn't have to be a monodisperse. It can be a bidisperse situation. And in this case, we can get, within a matter of a few seconds, the particles to segregate from one another, whereas in the bubble-free fluidization state, it was taking us maybe half an hour or several minutes to get the particles to segregate. Here we can do it within a matter of seconds. So with these Faraday waves, we like them because they're scalable and predictable, and we like the ability to get things done, the particles moving faster and segregating from one another faster. So that's what I just said, but we may want to ask ourselves, okay, what can we get particles to be moving around even faster, and can we get particles to mix rather than segregate? And for that, we move on to structured bubbling as a phenomenon. So as we see, if we blow gas up through particles, the gas can fluidize the particles and get these bubble-like voids to rise through the system. But if you don't have any vibration, you can see we're producing bubbles of all different sizes and shapes that are coalescing with one another. And this chaotic behavior of the bubbles makes it very difficult to scale up the system because all the bubble dynamics would change if we made the system twice as wide or twice as tall. We've shown that at a resonant frequency of 5 hertz, we can vibrate the system and it forms these triangular lattice bubble patterns where the bubbles don't collapse or bubbles don't coalesce with one another, and thus they stay about a uniform size throughout the entirety of the fluidized bed. And so already we like this because we're getting more predictable dynamics of the bubbles, and where we don't have we have scalability as well to the system. So if we make it twice as tall or twice as wide, we get the same bubble dynamics. And so what we can see here is that no matter what particles we put into the system, different densities, different sizes and such, 5 hertz always tends to be the frequency at which we get the most structured bubbling form. So this is a metric. The higher numbers mean more structured bubbling. So we have completely unstructured bubbling with no vibration, and then at this 5 hertz, for some reason, we get the most structured forming in the bubbles. And so what we did take a shot at was trying to see, can we find a simple way to model this, in this case as a harmonic oscillator, where you've got, where you have a drag force acting as a like pulling on a string, and then vertical expansion decreasing the drag force to act like the restoring force on that spring. And if what we aren't able to do is predict what this vertical spacing and bubble diameter is going to be a priori, but if we take that into account, that forms the relevant length scale for our harmonic oscillator model, and ultimately that can reproduce the 5 hertz in this frequency in this toy model of modeling the fluidized bed as if it were a harmonic oscillator. And so what we can also show is that using the CFD-DM simulations, where we're discretely simulating each particle, what we're able to get is we're able to reproduce this triangular patterning of bubbles in the system and the structured bubbling that occurs. And we see that the structured bubbling occurs because particles below the bubbles have strong contact forces in between them, meaning indicating they're in a solid-like state, whereas in between the bubbles, the particles don't have strong contact forces. So here they're in a solid-like state, here they're in a fluid-like state. So the next row of bubbles, when it forms, is going to form in the fluid-like region in between the two previous bubbles, creating this triangular lattice structure. So what we wanted to do is say that, okay, well, so again, we have a phenomenon where we've got solid-like behavior in the grains that leads to, and these transitions between fluid-like and solid-like behavior in the grains that leads to the structuring. Can we capture this with a continuum model? So using the rheological models built into the software and used in the literature for decades now, we noticed that we could predict a row of bubbles forming each vibration period, but we couldn't predict this triangular structuring that we see experimentally. And so we added in some more solid mechanics into the rheological model, and we were able to create a simulation which could reproduce, by capturing the solid-like behavior in the grains, this triangular patterning. And so when we looked at the simulation data, we could see that this solid-like behavior is inherently captured in the discrete particle simulations, and the strong contact forces lead to a higher effective pressure within the grains. And with our new rheological model, we were able to reproduce this higher pressure seen below the bubbles, which enabled us to recreate this triangular patterning. So again, we see an interesting experimental result. We note that it's occurring because of these fluid-solid transitions, and that inspires us to develop the rheological model better. And so we've also taken it a step further to incorporate heat transfer into our system, and we noticed that with the structured bubbling, if ultimately the goal is to get the most uniform particle temperature distribution in the system, we can see that, okay, you get a very uneven particle temperature distribution when you have a packed bed, but we get, if you have just an unstructured bubbling fluidized bed, you reduce that, you get a more uniform temperature distribution, but you get an even better uniform temperature distribution when you use structured bubbling. So again, for reactor purposes, structured bubbling we're showing can have some major advantages. And we can take particles that are very different in size and density, and we still get the structured bubbling pattern to form. And even if we put the heavy particles on bottom at first, the convection induced by the structured bubbling is strong enough to get particles to mix. So if we have a different application, such as in the pharmaceutical industry, where you need to get particles of different size and densities to mix with one another, structured bubbling is helpful for that. But if you needed to separate out the particles, you could go back to the Faraday waves for segregation, for example. So by tuning these vibration and gas flow conditions, we can get a variety of different patterns to form, and depending on what your use is, you can dial in basically the conditions to get the flow behavior you want in granular materials. So here's some of the takeaways. I'll try to speed up because I know we're running out of time. So we've got these fluid-solid transitions that create the structured bubbling, and we can get good mixing of particles to occur with them. And so we wanted to see, can we do this in other complex fluids, such as dense suspensions, and get structured bubbling? And so I'll just go really quickly through this since we're running out of time, and I want to be conscious of everybody's time. So what we've seen is that we can get bubbles to form in a manner where they coalesce with one another, always at the same red regions seen in the system, which if we look at the bubble area versus vertical position above the nozzle, we see these large increases in bubble area and very small windows because bubbles are coalescing specifically in these regions and not coalescing in other regions. And so we see this in a cornstarch water suspension, which has these transitions between fluid-like and solid-like behavior. And so if we look at this video just in its series of times, we can see every 131 milliseconds, bubbles coalesce in this bottom region, and every 262 milliseconds, bubbles coalesce in this middle region, and every 524 milliseconds, bubbles coalesce in this upper region. And so we can see that this is creating a pattern where at the top we've got a bubble that consists of what were originally 8 different bubbles at the bottom due to these 3 regions of coalescence. And so what we can see is that every 1.9 hertz, every 524 milliseconds, there's effectively reproducing the exact same bubble stream over time. And so, again, we call this structured bubbling phenomenon because the bubble patterns are not chaotically moving through the system. They're repeating in their structure over time. And so what we've shown as well is that shear thickening, so cornstarch water suspensions are a shear thickening fluid, and what we see is that the fluid surrounding the bubbles in these regions of regular coalescence is entering the shear thickening behavior, and that causes the bubbles to decelerate, the leading bubbles to decelerate while the trailing bubbles accelerate, and that leads to these patterns. So again, we've got a non-Newtonian rheological behavior that's yielding these structured bubbling patterns. And if we go to a Newtonian fluid, silicone oil in this case, we see that the bubbles coalesce, but they coalesce in a chaotic manner, and thus they don't have these regions of regular coalescence that we see in the non-Newtonian shear thickening suspension. And what we've shown beyond this is if we manipulate the injection time of bubbles, we can still get the structured bubbling to occur, but we can get bubbles of vastly different sizes forming over time. So if we manipulate bubble injection, we can further yield the structured bubbling. And if we manipulate the time in between bubble injections, we can also manipulate the locations at which we get the structured bubbling to occur. So again, for control of different chemical reactor situations, we get quite a number of different behaviors. And so all of this, just to give an example of more things we do, a lot of this we looked at in pseudo 2D systems, but we ultimately will want to look at it in 3D systems. So for that, we also developed techniques to use MRI to put the entire fluidized bed system in a medical MRI scanner and be able to image what's going on the interior of these systems. So for example, we can rapidly image the bubble dynamics going through the system using MRI. So there's other techniques we developed, and with MRI, we can look at not only where the bubbles are, but we can also measure directly the velocities of the particles. And we can do the same thing to look at bubble dynamics in dense suspensions. That's other work that we're developing. And some of the most exciting things that we're doing are being able to get not only a 2D slice through a 3D system, but take multiple slices and be able to create fully 3D images of the bubbles rising through a suspension, for example. And so you can see that when you see it in fully 3D, these bubbles often are not spheres or axisymmetric in any way, so you get more information by seeing the fully 3D images, for example. And so to conclude, this complex rheology and these fluid-solid transitions make granular materials very complicated to model, but also provide a lot of opportunities to manipulate their motion. And when you incorporate some of these fluid-solid transitions, you can get more accurate models of grains that can reproduce some of the experimentally observed phenomena. And we're trying to use the same principle with dense suspensions to see if we can manipulate bubble motion in dense suspensions. So with that, thank you very much for your time. I'd like to acknowledge some great researchers in my group who really did all the work that I showed here. And some of my collaborators on the MRI work are in Zurich and Hamburg, so I want to acknowledge them and acknowledge my funding sources. And with that, thanks so much for the invitation and for your time. Happy to take any questions.
Perguntas? Questions? Okay.
Okay, thank you very much for your presentation. Very nice, the research you are doing, these granular models. I'm very curious about have you tried to run your granular rheological model to reproduce that behavior that you have the binary split of your flow that you showed before? You are able to reproduce that with the TFM?
Yes, so we were able to reproduce the splitting in the end that we saw, but that we had, we had to play around with a few different parameters to get it to work. So I would say it's the rheological development, it's still all a work in progress, and I wouldn't say that we have it down to, no matter what we put in there, it's always going to accurately predict something or so. So it's still a work in progress, I guess, but we have been able to reproduce the splitting.
Okay, and you have some slides that could show the structure of this rheological model to show us? I don't think I saw the model equations.
Yeah, so I always forget to put in the slide. And it's on a different computer now. So
you can show that.
Yeah, happy to show you later. So I do have somewhere, but not readily available, unfortunately.
The structure of your model and how many parameters they have and so on.
Okay, yeah. So I unfortunately can't show you right now, but happy to talk about that later.
Okay, thanks.
Perguntas, pessoal. Fábio.
Hi, Chris. Thank you for your presentation. It was very nice, actually. So I haven't seen your presentation before, but I'm curious about, have you ever tried many fluids model to capture the rheological model? Because these two fluid models, basically, two fluids represent the distribution of particles. So instead of use D and M, why don't you use many fluids?
Many fluid?
Instead of two fluid model, you use like many phase to represent the particles. Let one size connect to another size and so on. They collide with different matter because they have different sizes. So have you tried it before? Have you ever seen it before?
For example, we do multi-fluid models is what we call it, where we do, so if we have particles of two different sizes or densities, we have one fluid for one type of particle, one fluid for another type of particle, and then a third fluid for the gas. So we have done that, but we haven't gone beyond three phases, but that's that. So, but it's theoretically possible. So we have been able to produce the splitting behavior in the three fluid model, in the multi-fluid model. But again, as I said earlier, it's we had to play around with a few of these parameters to get it to work. So I wouldn't say a priori it's going to be very reliable to reproduce things.
Temos tempo para perguntas?
Professor, thank you for your presentation. I have a doubt regarding your, why did you choose CFD-DAM instead of the most common approach like volume of fluid method to solve your CFD equation problem?
So CFD-DM, so the DM is used to model the particles individually. So we use that because it's a more accurate and can inherently capture both the solid-like and the fluid-like behavior. If we use, so the two-fluid model is very similar to a volume of fluid type approach, except for the fact that there's no surface tension between the two phases, and we instead have a drag force between the two phases used to model that. But I would say that the two-fluid model is fairly similar to what you would think of as a conventional volume of fluid in its model equations, and the fact that you're using CFD and Navier-Stokes type transport equations. But the difference is from a volume of fluid is that you've got a non-Newtonian rheology that you're using for your solids phase, and you've got no surface tension, and you have a drag force between the solid and the fluid phases. Does that answer?
Okay, more questions? Professor Nelly.
It was a very exciting presentation. I have just a small question. How fast is the MRI measurement? It seems to me very fast.
Yeah, so if we take just a 2D slice through the 3D system, we can get down to a 7 millisecond time frame between shots. It gets a little bit longer if we want to measure the velocity as well. That becomes more like 18 milliseconds. And then if we, for the 3D images, those I think, are more like 40 milliseconds or so. So there's always this balance between, how high the spatial resolution is and whether it's 2D or 3D, and then what the temporal resolution is. So there's always going to be that balance, but we have developed some techniques to, and a lot of what I showed, I should mention, a lot of that was developed at ETH Zurich by these two collaborators of mine, so I can't take full credit or anything like that for it. But yeah, those are the temporal resolutions we get down to, and that's sort of what you need to you can see the dynamics of these bubbles is very, very quick. So yeah.
We still have time for a couple of questions.
Maybe my question is more like an extension and maybe thinking over about collaborations. For example, images seem to be very important to understand your problem and classifying the instabilities. Do you think about using deep learning techniques to try to classify these images and help controlling the process, or even other approaches based on machine learning techniques to help improve the modeling for surrogate models, as CFD are usually very computational expensive?
So yeah, that's some of what Fabio and I have been collaborating on. I have very little expertise or knowledge of machine learning or other AI deep learning type of things. So that's why Fabio and I have been collaborating to try to see if we can come up with start with some of the CFD-DM simulations perhaps, and then use them to develop, put it all into some sort of deep learning technique to try to develop better rheological models for the two-fluid model. So that's something we've worked on, and happy to talk more with people with more expertise and interest in that area here.
Maybe tomorrow, Gustavo, that has just asked one question about the CFD, he will present some results that may be in this direction.
Okay,
Maybe
great.
Tomorrow we will have the opportunity.
Great.
Any more questions? If not, I'd like to answer Chris for your presentation. Thank you very much. Let's give him another round.
Thank you.
So Chris is going to be here until Friday. He's in room G 117. He's using Professor Papa's office for these days that he's here. So anybody who would like to talk to Chris in a more private environment, it's invited to just knock the door. He's going to be there, open to talk to you and interact to you.
If anybody wants to talk, invite him for a visit in your lab, you can talk to us and we can arrange, because he is going to stay until Friday.
Yep.
So we have time to do that. If we want to visit your lab, you see, it would be interesting. I'd like to say something, that this school that we are here is the kind of a birthplace here in Brazil for studies regarding granular materials. Yes, I'd like to remember his name here, because he was kind of the father here in Brazil of studies that regarded. And so in Brazil now there is, for example, Professor Marcos Barroso that works a lot, and maybe he is watching us today, I don't know, but so it is very interesting that now here you are presenting studies that you see pave the way for further studies. Very nice.
I I told him in the story about Professor Massaren, who created the particle systems area, and unfortunately he left us about 10 years ago when he passed away. And yeah, I mentioned him when we were taking a tour. All right. Thank you very much. Obrigado, and I'll see you guys later. Ciao.
No. What's that? Oh, thank- yes, yeah.